Now, if we look more closely on you, we might have noticed this when you do practical experiments, that although we've focused so far on the ray of light making its way through a semicircular block, but you can actually see some reflected light as well. And the other thing to notice in this experiment is we're starting from the curved side. So we're studying really the main bit. Remember, it goes straight through in the curved side. But when it reaches the flat side, it's going from the medium to air rather than air to medium that we had previously. And we're going to study an effect that happens there called total internal reflection. So just now what we've got is the light angle of incidence here is 30 degrees. And then it's coming out at 48 degrees. And we're getting a faint reflected ray coming at 30 degrees as well. The law of reflection is that these two angles should be the same. If I increase the angle of incidence, then you see the angle of refraction also increases. The reflected ray is always at the same angle. But because this angle here is always going to be bigger, the refracted angle is always going to be bigger than the angle of incidence, then it's going to reach 90 degrees before the angle on the medium does. Okay, and this is a critical point, and this angle here in the medium, when the angle in air is 90 degrees, is called the critical angle for that reason. And basically it's important because when we go beyond that, so not at that angle, but beyond that angle, then what we find is, well, this ray doesn't have anywhere else to go. It's reached its maximum right along the surface. It can't go to 91 because then it wouldn't be refracted, it wouldn't be in the air, it would be back inside the medium. And what we find is basically it disappears. And all of the light is now reflected, none is refracted. Hence the name total internal reflection. So total because all the light reflected because it's reflection, it's taking place. And internal because it happens on the inside edge, it happens when the light's trying to leave the medium. You can't get this effect going from air to the medium, always going from medium to air. So that just covers all that sort of stuff that we've said. And beyond that fact, we get total internal reflection. So the reflected ray just keeps following the law of reflection, always at the same angle as the incident ray in this case. Drop back below the critical angle, so their critical angle for this medium is 42. When we drop back below that, then you get back to a refracted ray and a reflected ray. Now, at the critical angle, we can apply Snell's law and derive a formula for the critical angle. So n is sine theta 1 over sine theta 2. Theta 1 is always the angle in air, so at the critical angle, that's 90 degrees, so that's a definition. The critical angle is the angle in the medium when the angle in the air is 90 degrees. So theta 2 becomes theta c, the critical angle is a special case for this formula. And the sine of 90 is 1, and so you can write that n is 1 over sine theta c, and rearranging that, we get a formula for what's called the critical angle, sine theta c equals 1 over n. In this case, the refractive index is 1.5, and it's a varied angle and confirm it's 42 degrees, as we'd expect. So if you plug the 1.5 in there, did the inverse sine, you get theta c is 42 degrees. From this equation, notice how the critical angle changes, the value for n changes. So if n increases, the critical angle will decrease. I.e. materials like diamond, for instance, which have a high refractive index, have a small critical angle, which means you get lots of reflection and therefore lots of sparkle. In general, total internal reflection can occur when light is incident on a boundary with a material of lower refractive index, but we've only looked at the case for when the other medium is air, and this formula only applies in that case as well.